2. Roman to integer. Given a Roman numeral, convert it to an integer. Roman numerals use specific symbols to represent numeric values, such as I for 1, V for 5, X for 10, L for 50, C for 100, D for 500, and M for 1000. One of their unique features is the ability to represent subtraction when a smaller symbol is placed before a larger one, as in IV, where I precedes V to indicate 4. The goal of the algorithm is to efficiently convert a Roman numeral string into its integer equivalent. This is achieved by traversing the string once and applying logic to handle both addition and subtraction scenarios. The first step in the conversion process is to create a dictionary that maps Roman numeral symbols to their corresponding integer values. This provides a quick and efficient way to look up the value of each symbol during the traversal of the string. Next, the algorithm processes the Roman numeral string one character at a time. As it traverses the string, it adds the current symbol's value to a running total. If the current symbol represents a larger value than the previous one, the algorithm adjusts the total by subtracting twice the value of the previous symbol to account for the subtraction rule in Roman numerals. The subtraction logic in Roman numeral conversion is applied when the current symbol represents a value greater than the previous symbol. In such cases, the algorithm subtracts twice the value of the previous symbol from the total. This adjustment accounts for the subtraction rule, where the smaller symbol preceding a larger one indicates a reduction. For example, consider the Roman numeral IX. The first symbol, I, adds 1 to the total, resulting in a total of 1. When the algorithm processes the second symbol, X, it recognizes that 10 is greater than 1, the value of I. To apply the subtraction rule, the algorithm adds 10 to the total but subtracts 2 times 1, the value of I. This results in a final total of 9. The algorithm is highly efficient in terms of time complexity. It processes the Roman numeral string in a single pass, making its time complexity big O, n, where n is the length of the string. This ensures that the conversion is completed quickly, even for longer strings. In terms of space complexity, the algorithm requires minimal additional memory. The primary storage includes the dictionary for symbol-to-value mappings and a few variables for calculations, resulting in a constant space complexity of big O, 1. This efficiency makes the solution both fast and memory efficient. Let's walk through the algorithm using the Roman numeral MCMXCIV as an example. The process begins by adding the value of the first symbol, M, which is 1000. This sets the initial total to 1000. Next, the algorithm encounters C, which has a value of 100. Since C is smaller than the following, M, 1000, it is subtracted from the total. To apply this, the algorithm first adds the next, M, 1000, but subtracts twice the value of C, 2 times 100, effectively adding 1000 minus 200 to the total. The algorithm then processes X, adding its value of 10 to the total. When it reaches I, it recognizes that the next symbol, V, is larger. It subtracts the value of I, 1, from V, 5, and adds the difference. After all these steps, the final total is 1994. Roman numerals use specific symbols, such as I, V, and X, to represent values. In some cases, smaller symbols placed before larger ones indicate subtraction, like IV, which equals 4. The goal of the algorithm is to convert Roman numerals into integers using an efficient single-pass approach. The conversion process starts by mapping Roman symbols to their integer values using a dictionary called Roman _to_int_ map. This mapping allows for quick value lookups. Next, the algorithm traverses the Roman numeral string one character at a time. If the current symbol's value is larger than the previous one, the algorithm subtracts twice the previous value to handle the subtraction rule. Otherwise, it simply adds the current symbol's value to the total. Finally, the accumulated total is returned as the converted integer. The algorithm is efficient in terms of performance. Its time complexity is big O, n, as it iterates through the Roman numeral string once, where n is the length of the string. The space complexity is big O, 1, because the algorithm uses minimal additional memory, requiring only a dictionary and a few variables for calculations. This makes the approach both fast and memory efficient.